Welcome to the last main topic of the class. As usual, we start with announcements, and now it is a pleasure to announce the remaining exercises for this term, of which there aren't many. So there's a homework that's due this Thursday. As always, you can submit it by Wednesday for bonus points. Project 3 has been released. This week, we will be covering everything that you need to do project 3, though you could, a lot of it is data manipulation, which some of you have already started on, doesn't need what we're teaching this week. So it's been released. The checkpoint is on Friday. And as you know, that you're just, that's just to make sure that you've gotten started. You can go back and change things later. The project is due the week after Thanksgiving. So you have a good long time to do this. And even if you take the Thanksgiving break off, which I sincerely hope you can do, you'll have plenty of time. Lab this week is working on the project. And then there will be a homework that will be released this Friday. That is the last homework. Will correct me if I'm wrong. I believe that is the last homework. And that will be due after the Thanksgiving break. We really didn't want to make anything due the night of Thursday, Thanksgiving. And the very last lab will be released after Thanksgiving. That's a fun lab. And that's it. So questions? All right. So what we're going to do today is start the discussion of classification. Before we get into details, let's just take stock of where we are in the class. So the first third of the class, we taught you how to describe the data that you have. Right, so you learned how to work with the tables of data, you learned how to visualize, you learned how to interpret visualizations, you learned how to combine two data sources to get more information and so on. In the middle third of the class, we started to discuss how we can generalize our conclusions to bigger populations, how we can make inferences, how we can check whether what we are seeing is just noise or whether it's actually reflecting something real. So you learned about testing hypotheses, you learned about making confidence intervals and so on. And now in this last third of the class, we are focusing on making predictions. And we spent the past couple of weeks talking about regression as a method for prediction. And we had an assessment of, whether the regression is any good. And we were able to draw general conclusions based on the regression that we've done for a particular sample. And now we will talk about another kind of prediction, which is called classification. And so today we will talk about it in general. We'll look at a lot of examples. Today we will not focus on any code, though there will be quite a lot of code in the demo. We will just ignore all of it. Much of it is just for visualization. But the code, we are going to write a code that takes individuals for whom we have a certain amount of data and classifies them into one category or another. And so Wednesday and Friday will be focused on that. On Wednesday, the main focus will be building a classifier. And on Friday, the focus will be on how good is it? Assessing the accuracy of the classifier. And, it probably won't be as separated as that, but in general, Wednesday and Friday, you'll build a classifier and assess its accuracy. So step back, we should look at our approach to prediction, which is going to be the same approach that we will use now. So we are trying to guess the value of some response, which is one of the attributes of the data. And we have only incomplete information. We don't know what that value is. So perhaps what we have is some historical data, right? So in the past, we had individuals like this, And we knew many attributes related to those individuals, including the one in which we're interested. And now along comes a new individual, and we have to make a prediction. So one way is to predict an outcome from this new individual. You find others in your historical data set who are like this individual, right? So for example, when we were doing regression predictions of a child's height based on parents' heights, so we had this new family that showed up and they had the two parents and a baby, and we were trying to predict the eventual height of the baby. What we did is we looked at our historical data set, and we had an assumption that the parents that are coming to us are somehow like that historical data set. And in that historical data set, we had not only the parent's height, but also the child's eventual height. So we were able to use that information to make a prediction for the new individual by looking at parents who were like the parents in this new family. So we use those past historical data and the known values of the attributes as the basis of the prediction. Now, in this class, we'll cover two types of prediction, one of which we have already done, that is regression. Now, in regression, what did we have? We had two numerical variables, and we were trying to predict one of them based on the other. What we're going to do now is look at the case where the variable we're trying to predict is not numerical, it's categories. Right? And the most common case is the one we're going to focus on, which is where there are two categories, yes or no. So classification means taking an individual for whom you have a bunch of attributes and classifying them into one group or another. And so that's the project that we are engaged in this week. And what I'd love for you to do is to classify some of my emails. Okay, so spam or not. And what I've done is I have a sequence of examples of, you know how when you go into Gmail, there's a little snippet that you see, that first line in your whole list of emails. So I just took screenshots of a few of my emails from the past few months. And what I'd like you to do is look at each one of them and in the chat, say whether you think it is spam or not spam. And for now, I'll allow you to say maybe, but later on, we are just going to force a prediction one way or another. Okay, so here's the first one. Spam or not? Boom, the chat explodes. Everybody's saying spam. Okay, so this one was in fact spam. Yes, exactly. And so somebody is saying, okay, look, there's that misspelling there and so on. So you've used some, your background knowledge to make a judgment here. How about this one? Spam or not? Okay, this is, the votes are hugely for not spam, but there's a bunch of maybes as well, right? A bunch of maybes, could be, unsure. And in fact, this was spam. This was some outfit of which I was not a member, would just send me an email saying, oh, you know, your memberships, here's what you have. It was spam. And look at the difference between your confidence in the two decisions, right? In the first decision, you are very confident. That thing is spam, right? So sometimes you just, you're very sure about your accuracy. The second thing, many of you thought not spam, some of you were unsure. There's much less certainty about the decision. And in fact, it turned out to be spam, this one. So what you can see is you have incomplete information, and sometimes even with incomplete information, you're very sure and sometimes you're not. Okay, how about this one? Spam or not? This is not spam. And this, the reasons so many of you are saying not spam, everybody's saying not spam, is because you kind of know what kind of emails this professor gets. And that is very clearly something you know a lot about. You know a lot of similar conversations. And so you're very confident here once again. And here's another. Oops. Okay, spam or not spam? So spam. Overwhelmingly, you're saying spam. This is not spam. There is actually an app called Yes, it is an app which has this cute name. And what it does is it helps us create videos at home. So nice quality videos. So because is a cute name, every other update that they want to create also has a cute name. So one of them, I don't know how to pronounce the I don't know. Okay, so this thing looked like spam, but it actually is not spam. Right, I'm signed on to this app on the advice of my colleagues in computer science, and they send me information from time to time. This is not spam. All right, so look at the second and the fourth ones, right? You can see errors of both kinds. The second one kind of looks maybe like not spam, but it actually is. And the fourth one kind of looks like spam, but it actually isn't. Okay, so you can see that you're because of incomplete information, we can get things wrong. But what we are doing in our heads is we are comparing this little snippet that we are seeing with similar emails with which we have experience. And depending on our experience, we make a decision which is good or bad, depending based on how rich our experience is. And this that we have done by ourselves reading something and thinking about what we already know is done by machines on huge scale. And so here's a very common example: fraud detection. So supposing you make a purchase on Amazon or some big internet site using a credit card, then before the stuff is sent to you, the online that the outfit needs to know whether this is actually a real transaction, it's you buying it on your credit card, or somebody maybe stole your credit card and is trying to buy something. And so they have to quickly go through millions of transactions. And if they've been running for a while, they have a record of transactions that were fraud and transactions that were not fraud. And they will try to see whether this transaction resembles the fraudulent transactions or the non-fraudulent transactions. And when I say they, I'm not imagining some kind of human Wizard of Oz behind a curtain reading all of these transactions. It's a machine. All right, so the machine goes through lots of transactions and just checks for things like, is the billing address the same as the recipients, the sending address, the mailing address? Is this a very different kind of object from what the person has previously bought, and so on and so forth? Lots of attributes are being compared, and then it is making a decision. So this is not something that is going to be done by humans because of the massive scale, but it's important that it's done because fraud costs everybody, right? It costs the organization, and by extension, it then costs us because prices go up. And of course, you want to deter criminals. So this is an example of classification. Here's another. There are dating websites so that try to match people based on their criteria. And so people who join these websites put in certain information about themselves, and now there are millions of such people. And so there is machine learning which is a way of doing classification that is applied to all of these data. And so to a particular individual, what we're trying to do is to find all of the other individuals that may be a good match for this person. Now I'll say something. You know, when we see all this, we see Amazon, credit cards, fraudulent transactions, computers, machine learning, it all seems very modern. But look at the second example of who matches with whom. Yes, the dating websites are, of course, all post-internet, and there's lots of them now, but they are really standing on the shoulders of giants who have been doing this for, well, I would say a very long time. And those giants are known as aunties, right? Do you know, in many communities, there are people who just know all about all young people, right? Whose son or daughter is, or whose child is interested in, you know, maybe getting married and so on, and where they went to college, and whether they are tall or short, and this, that, and the other. There are people who know, in my view, far too much, far more than they need to, about everybody in the world, and then they match up, right? So what's happening is we now have the machine version of that. And the other thing is that in the machine version, the individuals themselves get to type in what they would like the world to know as their characteristics. So that's also different. But really, this is, you know, on a large scale, something that has been done for a long, long, long time. Something that is relatively newer and very powerful is the use in medicine. So a few years ago, there was an example. There was an exercise done in dermatology, where somebody took pictures of lesions on people's skin. So, you know, it's like imperfections and so on the skin. And the goal was to see, is this serious, right? Is this perhaps cancerous, or is this benign? And those pictures were somehow quantified, right? They were described numerically and fed to a classifier, to a machine learning system. And that system had historical data. It had historical data on pictures of patients for whom it was known whether that skin condition was cancerous or benign. And what it did was it took the new pictures and it sort of matched, right? This new picture kind of looks like this other picture, and this one turned out to be benign. So I'm going to conclude benign for the new picture. It did exactly what we said we were going to do, which is this: for the new individual, you find individuals in your historical data who resemble this individual, and then, you know, you make the prediction, which is sort of the typical prediction for those similar individuals. So this particular algorithm happened to do better than the two human dermatologists that were shown the same pictures. But that doesn't mean that dermatologists are obsolete. The algorithm aids the dermatologist, right? Because after this decision is made, the dermatologist has to decide on a treatment. And sometimes the dermatologist might disagree. And then, you know, you need that human intervention as well. But it's a good aid for the medical profession. And our main example, Wednesday and Friday, is going to be identifying whether cells are cancerous or not. Those are not skin cells, but it's a similar example. Okay, so these are very powerful methods. They can take in a lot of data and they can spit out a prediction. Okay, and in some sense, it feels like they're objective in the sense that they're data-based, what is fed into the process is the historical data, right? So all of the attributes, including the response of the previous patients, and some kind of criterion for what similar means, right? So when you take a new patient, in what way do you define similar to other patients? But there is no indication of which attributes to use and which not to use. The machine discovers that by looking at the sample in ways that we'll see in a little bit. So in that sense, it feels very objective. However, nothing is actually objective. Everything that involves data involves human beings as well. And we have significant potential for bias. So here is a headline from a Wired magazine, and this is all, these discussions are very, very current over the last 5 years or so. There were algorithms that were supposed to fix the bail system, but they haven't. So the Pretrial Justice Initiative, this is a nonprofit organization that was interested in fairness, especially across different racial and ethnic groups, in the bail system, right? So if somebody's accused of a crime, then until they're, while they can get bail, until their case goes to trial, until there is a resolution, they can get bail, or a judge can deny them bail. And so what was noticed was that judges have biases. And so the idea was that if you use an algorithm to decide whether somebody should get bail or not, that might be more fair. Except on examining what the algorithm did, it was not more fair. In fact, in some cases, the disparities increased. And so now the same organization said, you know what? No, let's bring back the human beings. You can't do it just with the algorithms. And why is that? Because the algorithm is starting with historical data, and it's basing its predictions on that. Now, if historical data include bias, right, which they do, for the same crime, if you were from one racial group, you were more likely to get bail than if you were from another racial or ethnic group. Then what does the algorithm see? The algorithm sees, this kind of person, this ethnicity does not get bail, typically. So I will not predict bail for this person. What happens is that the racial bias that is baked into the sample data then almost gets reinforced by the algorithm. And that's a real problem. So also, if you were in algorithms used to improve healthcare, racial bias can get reinforced. For example, it's not just racial bias against various groups. Women have tended to be undertreated for diseases like heart disease, and especially women who come from minoritized racial or ethnic groups. You go in with chest pain and you're told, oh, you have indigestion, here's an antacid, go home. So now if the data already have that bias in them, that is, this particular demographic group does not get treated for heart disease, then the algorithm is going to predict that they should not get treated for heart disease, and you just have a reinforcement. Also, we have to decide what attributes we are using and how they are being quantified. And you'd like to use attributes that are associated with what you are trying to do. If you're trying to improve healthcare, you want to use attributes that you think are associated with improving healthcare, but you guys all know about confounding, right? You could use an attribute, but it's actually reflecting something quite different, and sometimes the causality can be reversed, all right? And so the many questions that are popping up in the chat are all in the direction of what could we do to fix this. And we in this class are not going to get deeply into that, but wouldn't it be nice? Wouldn't it be nice to hear from some of the experts on what the issue is and what can be done to fix it? What do you think? Would it be nice? Anyone interested? A number of people are interested, so we're trying. Hold that thought. We're trying to get, in fact, one of the people on this screen, we're trying to get them to come to Data 8 this term and talk to you about this bias. Maybe by the end of this week, we'll know if and when that's going to happen. So at the moment, I am predicting coming soon to a Data 8 Zoom screen near you. We'll have more discussion about the bias. Okay, so the message here is these methods are very powerful, but with great power comes great responsibility. And we have to use the methods ethically and understand the innards of what they're doing. Okay, so now we're going to talk a little bit more in detail about classification. And, you know, data come in many forms. So we just talked about spam versus not spam. And so here you're going to take a message and classify it as spam or not spam. There are two categories. And so this is called binary classification. And this is by far the most common. And that's the one we are going to be focusing on in Data 8. Now, messages don't have to be text. They could be pictures. So for self-driving cars, the kind of picture that you see, imagine you're in a self-driving, you are trying to design a self-driving car. Then if you're driving the car, the human being will see the picture on the top. And the car, it's a machine, sees pixels, right? Which look maybe like the picture at the bottom. And now it has to classify all of those different pixels into groups. What's the sky, what's a tree, what's a stop sign, and so on and so forth. So lots of different categories. And here is a picture from what it looks like in the camera of a self-driving car. And you can see that it has blocked off groups of pixels. And so this group of pixel is one block, a sort of 3D block, thinks it's a car. Here is something in red, that's a stop sign. It's concluding stop. And it has to decide, you know, is there a little kid, or is that just, you know, some other thing on the road? What do I have to do? So this classification is very, very important. And the accuracy of this classification is hugely important, which is why it's not just enough to have a method, but the method has to be very accurate. And so what we're going to do now is we're going to look at a notebook. And so before I jump into the notebooks, today, there's going to be a bunch of code, but we're just going to ignore all that. All right, today we're just going to look at the main methods. And then Wednesday and Friday will be spent looking very hard at both the method itself and its accuracy line by line, how to set up the building blocks of your calculation, and then how to code. Okay, so what I'd like you to do is to get to this point of the demo notebook here and just hit run all above. Because there's a whole bunch of functions and so on we've defined. And the first example we're going to start with is a data set that was collected at a medical practice, and it has data on 158 patients. And the issue was, do they have chronic kidney disease, hence CKD, or not? Okay, so each row represents a patient, and there are a bunch of measurements, the age, blood pressure, etc. And there's a whole lot of blood tests. Glucose, sodium, potassium, results of their blood test. And at the very end, you can see there is this thing called class. All right, so this is the category, and it's a 1 or a 0. 1 means has chronic kidney disease, and 0 means does not have chronic kidney disease. So this is the historical data set that was available at this medical practice. And what we're going to try to do is to see if we can take this historical data set, imagine a new person, and look at all their attributes. We won't have their class, we have to predict their class. So just to get a sense of the previous data set, if we just group by class, then in the data set, 115 people did not have chronic kidney disease and 43 people did. Okay, now there's a whole lot of variables here. We're just going to do some exploration. Okay, so we are just going to try to look at the relation between the white blood cell count and the glucose in the blood tests. And there's one more variable. Okay, so there are actually three variables in this picture. On the horizontal axis, you have white blood cell count. On the vertical axis, you have glucose. The third variable is the class, which is represented as a color, right? So here's a scatter diagram. Now, based on this, we're going to try and make a prediction, right? So I have a new patient that comes along, and my cursor is going to represent the data about their white blood cell count and their glucose. So the new patient comes along, and they're here, where my cursor is. So, you know, their white blood cell count maybe is around 130,000, and their glucose is maybe, oh, I don't know, 270 or something like that. What prediction would you make for this person? Would you predict class 1 or class 0? So look at the legend. Okay, so the gold is class 1, and class 1 means they have chronic kidney disease. So are you predicting 1 or 0 if the patient is where my cursor is? Has the disease or does not have the disease? What do you think? Has the disease. You're predicting gold. Why are you predicting gold? It's closer to the gold. Yeah, if you look at all the points around it, the nearest neighbors, sort of the similar points are all gold, right? Blue almost never goes there, exactly. So you're actually reasonably confident even in this prediction, okay? What if the person was right here? So right at the bottom. So their glucose is really low and their white blood cell count is maybe just at 100,000, just low. What do you think? If I force you, I'm going to make you, I'm going to force you to make a decision. 0 or 1, you have to make a prediction. What are you going to predict? Yes, you're going to take the better of the two. All right, you're going to take the better of the two, and the better of the two appears to be blue because the points around it are blue. And the reason you are worrying, what is the reason you're worrying? You were very confident with the previous one. What is the anxiety about this one? There is some yellow nearby. Exactly, there's this overlap. All right, so in this range, the patients with the disease and the patients without the disease sort of look similar in these two variables. Right? They may look different in other variables, but in these two variables, they look similar. So we are less confident about our decisions, our predictions in this range, right? And that's a fact about making decisions based on attributes. Like when you have the attributes are sort of very mixed up between the two groups, then your decisions could be less accurate. So one thing we can do is to try to find some other, but there's a lot of variables in the data set. We could try to find some other data set, some other variables that will make our, that might make our decision easier. So we're going to look at, instead of white blood cell count on the horizontal axis, we're going to look at hemoglobin in the blood. And do the same thing. So we still have glucose on the numerical axis, and now you have, and the same colors for does not have the disease and has the disease. And now this is a little better, is it not? Why is it better? Why is it easier to make predictions with this? There's virtually no overlap. We got really lucky. Right? We got really lucky. There is, I mean, essentially, if the person is in this range where my cursor is, you're going to predict blue. And if they're outside, you're going to predict gold. And there's really no yellow points in here that I can see. And so we feel much more confident about our prediction. Okay, so now what I'd like you to do is I'd like you to build a classifier. What is a classifier? A classifier is a function. I give you a new person, and you have to tell me blue or gold. Does not have the disease, does have the disease. That's what you have to do. So it's a function. It will take the hemoglobin and glucose of a new patient, and it is going to spit out a prediction. Okay, so what kind of rule that could we use just based on this thing being roughly a rectangle? What kind of rule could you use? Can somebody suggest a rule? 2 if statements is a great idea. is a wonderful idea. So could you elaborate on that a little bit? Okay, let me start you out. If the hemoglobin count is, continue the sentence, please. If the hemoglobin count is greater than, say, 12.5-ish, and what's the other one? And if the glucose is less than about, I don't know, what is this, 130 or so. In other words, if the patient's point is in this rectangle, then what are you going to predict? You're going to predict class 0, does not have the disease, right? If the patient's point happens to be roughly in this rectangle, you're going to predict does not have the disease, and otherwise you are going to predict 1. Okay, and somebody's even written the code, and that is your, exactly, this is your sort of skeleton code for this. That is exactly what you're going to be doing. And so, I mean, that's great. And if the person happens to fall here, you're going to make a great decision. If the person happens to fall here, that's just skeleton code. I wouldn't worry about the details of the code. If the person happens to fall here, you're going to predict gold. If the person happens to fall here, what then? You might be a little bit worried, right? Because maybe your sample isn't big enough. Maybe there are blue points there, you don't know. But what you have done is you have built a classifier. You have built a rule. But that rule depended on our eyes seeing this rectangle. But I mean, it's no human eye is going to be looking at it, right? There's going to be lots of attributes. A machine has to decide. So we have to do something that a machine can do. And so now what we're going to do is look at another example. And we're going to look at data on banknotes. Somebody took pictures of banknotes, fraudulent banknotes and real banknotes, and looked at attributes of these. And our job is to, this is the historical data set. We know which ones were fraudulent or not. Our job is to identify which ones are fraudulent and which ones were not. Okay, so now what I'd like to do is I would like to start thinking like a machine. Okay, so here we have all of these data and we kind of understand hemoglobin, glucose, it's in the blood. Now we are going to think like a machine. The machine just sees the numbers. The machine doesn't actually understand what the variables mean. And so we also are not going to understand what the variables mean. Here are the data on the banknotes. Okay, so there's 1,372 banknotes were classified. 0 means zero means okay, and 1 means fraudulent. And what mathematicians have done is that they have taken pictures and learned how to code them mathematically. And so these numbers are wavelength variance, wavelength skewness, wavelength kurtosis, and something called entropy, but we are not going to understand any of those. It's clearly beyond the scope of this class, but nor does the machine. Okay, so we are just going to say, okay, can I use these variables at all? And so I'm just, what am I going to do? I'm going to do what we did before. I'm just going to take 2 of the variables, this one, the first one and the third one, and I'm just going to group by class, and I'm going to see what I get. Okay, so here, is it easy to make a decision between the 2 classes? What do you think? So yeah, people are saying no, because here in this range, yeah, it's pretty clear, but there's a lot of overlap here, right? So this is not as comforting to make a decision based on these. So we just tried another one. And we have these 2 scatter diagrams. And so now, okay, so here you're pretty clear, but here looks like some overlap, and here looks like some overlap, but here again, you're pretty clear, and this looks worse, does it not? Right, there's a sort of more overlap. Okay, but now what I'd like you to do is I would like you to indulge me a moment, because I looked at these 2, the yellow and the blue scatter diagram, and in my head, I saw dolphins. So I'm going to take you to the dolphin world. Okay, that's what I saw. Take a look at that picture. Okay, how many dolphins do you see? Yeah, you see 2 dolphins, all right? Because you know what dolphins are. you know, heads, tails, and so on and so forth. You're seeing two dolphins. But if the machine saw this, it would look at these pixels and it could be forgiven for thinking that these pixels all represent one object. And so what we're going to do is we are going to actually look at mathematically at what our eye is doing when it decides there are two dolphins. And we're going to pretend that we don't know about noses, tails, fins, and so on and so forth. Okay? So what is our eye seeing in this picture? It is seeing a few attributes of these pictures, of this diagram, which is that for each of these dolphins, there is a left-right attribute, right? If we're standing and looking at it, there is a left-right attribute. And so for both of these dolphins, they're very similar, okay? And that is one of the reasons for a huge overlap. So in the left-right attribute, there's a lot of commonality between the two. Now, there's another attribute that is the up-down attribute. There also, there is a lot of commonality. They're not exactly the same, but there's a lot of commonality, and that leads to overlap. In this picture, from this vantage point, we are seeing those two attributes, and we have a lot of overlap. But is it not true that when we look at these dolphins, immediately our head says one of them is sort of behind the other from our perspective? Yes or no? Yeah, so if you imagine yourself standing at the beach and you're looking out to the sea and there are these two dolphins, then this one is behind this one. And what you're using is a third attribute. You're using depth. It is the distance away out to sea from where you are. That is the third, front, back, exactly. The third dimension is what you're using. And if you could see that third dimension, maybe if your vantage point allowed you all three dimensions, then the picture might look something like this. Right? And so introducing that third dimension helps you see the separation. And that's exactly what we're going to do with the banknotes. In the banknotes, we used two variables to draw our scatter diagram, but we had other variables in our data. We had other attributes in our data. So going back to the banknotes, what we're going to do now is we are going to use three of them. So we're going to keep, we're going to use the first three. 1, 2, and 3, and see what happens when you use three variables instead of two. So three attributes. And if I run this, now suddenly you have a separation. So what you're learning here is sometimes introducing another attribute can help you see separation. And so when you work with data, you're going to be working with multiple attributes, not just two. Because sometimes you more attributes will help you find a separation. All right. So are we ready to do a little bit of actual classification? That is essentially the end of my slides. I just want to spend the rest of the time doing a demo. We good? Okay, so what we'll do is today we're just looking visually, so we will just work with two dimensions. Yeah, we're going to use two attributes, and this will help set us up for what we're going to do later. Toran, you're absolutely right. We can make a plane of division. Okay, so we're going to go back to our data, and we are going to restrict ourselves to the three. There's a ton of variables here, some of which are strings, categorical, some of which are numerical. Okay, so we're just going to restrict ourselves to a very small number of variables: hemoglobin, white blood cell count, and where's glucose? Glucose is somewhere right here. Okay, if you look at those variables, they're all on different scales. Right. And one thing we don't want to do is get messed up in the scales, and some numbers are very large and some numbers are very small. We're going to put them all on the same scale, and therefore you can see at the bottom of the table what scale are we going to use. When we want to put them all on the same scale, we're going to put them all in standard units. And so I've reduced the table to this. I have hemoglobin in standard units, glucose in standard units, white blood cell count in standard units, and then the class is the same as before. Okay, so if I show you the hemoglobin glucose scatter diagram, it's the same as the scatter diagram we had before. It's just you have standard units on both sides. And this is a move we've made over and over and over again. Okay, all right. So so what we're going to do now is we're going to build what is called a nearest neighbor classifier. If I take a person here, right, what you told me is I should predict gold. Okay, and in some sense, it's because the nearby points are gold. So we're going to take the simplest version. We're going to say, okay, we take my new point, find which point in my historical data set is closest to that, and my prediction will be the color of that closest point. And if 2 points are exactly equally close, you can just toss a coin, it doesn't matter. That's very unlikely that that's going to happen. All right, so the goal is this. We are going to take our new point and find its nearest neighbor in our sample, okay? And if that nearest neighbor happens to be gold, we're going to say gold. And if that nearest neighbor, if our point is here, the nearest neighbor happens to be blue, then we're going to say blue. That's a classifier. And so I'm just going to run a cell that does some classification for me. So nearest neighbor approach is you plot the new patient's data on your scatter plot, find the sample point that is closest, and your prediction is the color of that historical point. Okay, so here is a little visualization. My new patient has their hemoglobin is average, so their hemoglobin is at 0, and their glucose is 1.8. All right, so this red is the new patient. And what the function has done is it has found the closest point, and the closest point happens to be this one. So what is the prediction for this new red patient? What is the prediction? Gold or blue? Gold. You're predicting that they have chronic kidney disease. Okay, and so obviously we can change this patient. And so now if the patient still at average for hemoglobin, but their glucose is now lower at 0.5, then the closest point happens to be blue, and you will predict blue. Okay, so now can we change a little bit? Can you give me a couple of, make up a new patient and let's see what happens with the prediction. Anybody? -1 and -0.05. Okay. -1 and -0.05. Okay, so -1 and -0.05, the closest point was that one there. And so we are going to predict gold. Okay, so you can play this game over and over again. And now so you can see what is the machine doing. We can see if my patient is here, then I can see that there's a gold point very close by. And so I'm going to pick up gold, but the machine cannot see. So what the machine is doing is it is actually calculating the distance between this point and each and every one of the other points, and then doing a sort and finding which is the smallest, and then using that one as a prediction. Okay, and so we are going to do that. For every single patient, we're going to build a classifier. Okay, so the gold and the blue points are our historical data. And what are all these red points? All these red points are where a new patient could possibly be. And yes, if you do it on a finer scale, you'll have more red points, but I've just written down all possible new patients, okay? And what our method has to do is make a prediction for each patient. And I'm actually going to run my next cell because it takes a while to chug, and I'm at 2 minutes. So, okay, for this patient, right here where my cursor is, what is your prediction going to be? What's the nearest neighbor, gold or blue? Gold, so what's your prediction going to be? Gold. So around here, you can see that the predictions should be gold. What about here in this corner? They should be blue because these points are clearly closer to blue points than they are to gold points. What about right here? Not so sure. You'd actually have to compute some distances, right? Is it closer to this point or is it closer to that point? So you have to figure out here, the distances actually matter. If the point is here, your prediction is going to be gold, but as you come down, at some point, this blue point becomes closer and your prediction is going to switch to blue. But at the end, how many colors are you going to have on this graph? Yeah, you have gold and blue. You will only have gold and blue. You will have made a prediction for each and every person. All right, and that is what the next cell is doing, and it is done, and here is what has happened. So for each person, what we have done is we have computed all of the distances, found the closest one, identified the point, and made that as our prediction. And so now you know what you have done is you have built a classifier, right? If I give you a new person, then the new person is going to be one of these dots. And you have already told me blue or gold. You have built your classifier. Now, the question is, what is it any good? One thing to note, a little bit of language. Here, your decisions are gold. Here, your decisions are blue. This separating line, which we are lucky we have a separating line because we have no overlap here. This separating line is called a decision boundary, right? It's where your decision switches. And so now there's a lot of questions. And that is why we have a couple of other lectures on this topic. So I am going to stop here and